So welcome to the 39th Theoretical Physics Colloquium by Professor Elena Bratkovskaya from the Theory Division at GSI Darmstadt and John Professor at the Institute for Theoretical Physics at Johann Wolfgang Goethe University in Frankfurt am Main. She received her PhD in 1992 from Bogoliubov Laboratory of Theoretical Physics at Joint Institute for Nuclear Research in Dubna, Russia. She got her habilitation in 2004 at Goethe University in Frankfurt am Main. She had several postdoctoral positions after receiving PhD in Dubna, Gießen, University of Gießen, University of Frankfurt, of Goethe University in Frankfurt. Then she became a fellow, a junior and a senior fellow at FIAS, Frankfurt Institute for Advanced Studies. She became a tenured research fellow at IDP and FIAS in Frankfurt in 2009. Since 2016, she is a senior researcher, permanent researcher at GSI in Darmstadt. Over the years, she was participating in many professional service activities. She is a member of NICA White Paper Editorial Board at Joint Institute for Nuclear Research in Dubna. She was, between 2012 and 2018, head of the physics board for the experiment baryonic matter in nucleotron in Dubna, and between 2016 and 2020, she was a Germany representative member in the management committee of the European Cooperation in Science and Technology Action on Theory of Hot Matter and Relativistic Heavy Ion Collisions. She has a wide research interests in heavy ion physics, phase transitions from hadronic to Partonic matter, properties of quark-gluon plasma, dynamical transport theory, for the descriptions of hadrons and partrons, dilepton strangeness, chum production in heavy ion collisions, hadron properties, and many other things. Today, Elena will be talking about exploring the QGP at finite baryon chemical potential in and out of equilibrium. And with that, I'll give the microphone to Elena.
Igor, thank you very much for your introduction and of course for the invitation to give a colloquium here. And I'm really very grateful to all of you who decided to join this colloquium today in spite of some other very important event. Okay, but let's come to physics event today, and I definitely will try to give you some kind of overview what we did in our group on the topic of QCD at finite baryon chemical potential, and give you example in equilibrium in terms of calculation transport coefficients, and also show the result for heavy ion collisions and so on. But let me start with some general introduction, since I was told to, let's say, make the talk achievable also for young members and for students. So, and let me remind about the main goal of heavy ion collisions, heavy ion experiments. In heavy ion experiment, we are trying to recreate the condition of Big Bang in the laboratory. For that, we put matter at higher pressure, and that we heat our matter such that we create a quark-gluon plasma, the matter which contains of deconfined quarks and gluons. And this is a condition which is coming back to the beginning, to the early stage of our universe. But in order to recreate such condition, we have to perform a very complicated experiment and build heavy ion accelerators. And as you well know, nowadays we have two actively working machine. It's a Large Hadron Collider at CERN and relativistic heavy ion collider RIG at Brookhaven. And there are two machines, which is a FAIR and at Darmstadt and NICA in Dubna, which are presently under construction. And with the help of heavy ion experiment, we are hoping to explore the so-called phase diagram of QCD, which reflects the thermal properties of QCD in T and mu B plane. Here you have a temperature, here you have a baryon chemical potential or baryon density. And in the early universe, we had a matter with the prior zero baryon chemical potential and at a very high temperature. And such condition, similar condition we recreate by LHC experiments, but then by varying the energy of colliding heavy ions, we can go down in terms of the temperature, but however, explode different phases of baryon chemical potential. And here you see, of course, it's a statistic view, different trajectories which are achievable by different experiments. Here we have RIG and then CERN experiment in A61, and that is the future experiment Nika and FAIR. And at very low phase, we have a present experiments at Hades, at Darmstadt also. And what we hope to study, that's of course equation of state of dense matter and the possible phase transition from the quark-gluon plasma to the hadronic gas. And we wanted to understand how this transition happens, if it's a crossover, as we know presently for very high energy heavy ion collisions, which are crossing the phase boundary in this direction, or this might be some first order phase transition with a possible critical point. Moreover, there are many other interesting features like chiral symmetry restoration and modification of the properties of hadrons at higher baryon density and temperature, which occurs already on the hadronic part of the phase diagram. And of course, how do we know, how we obtain information from heavy ion collisions? We have to look for the different signals of the phase transition and for different observables. And there are many of them, and they're related to the measurement of the final hadrons and leptons. And that is the main problem, that of course, what we measure in experiment and the final hadrons and leptons, we cannot measure directly quarks. And by having this information about hadronic and leptonic degrees of freedom, we have to trace back in time the history of heavy ion collision. And of course, we cannot do that without comparing the experimental data with the theory. For that, we need a theoretical model, theoretical background for description of heavy ion collisions. And here there are three basic models for the heavy ion collisions. First of all, it's statistical models. And they are based on the assumption that system is described by Grano canonical ensemble of non-interacting fermions and bosons and thermal and chemical equilibrium. Roughly speaking, you consider the thermal gas at freeze out with common temperature and baryon chemical potential. And if you look on the small picture and which shows the time evolution of heavy ion collisions, you just consider basically the final stage of the reaction after freeze out, and there is no any dynamical information in such type of model. There are hydrodynamical models which contain dynamical information because they base on assumption of conservation laws plus equation of state. However, they need assumption of local thermal or chemical equilibrium. And in this case, the interactions are somehow hidden in the properties of the fluid, which is described by the transport coefficients, which I will talk later about, such as the shear viscosity, bulk viscosity, and they are all input for Hydra models. So in this case, you have simplified dynamics in terms of the fluid. And there are a third class of model, which is a microscopic transport model. They are based on the transport theory of relativistic quantum many-body system. And in this case, we explicitly account for the interaction of all degrees of freedom, hadrons and partons, in terms of cross-sections and potential. And only using the microscopic transport approaches, you can obtain information about dynamics of strongly interacting matter in and out of equilibrium. And in this case, in equilibrium properties could be expressed in terms of transport coefficients, which are calculated in this case directly. You can simulate in heavy ion collisions in the infinite, you can simulate, sorry, with the transport approaches, the infinite matter, but putting your, let's say, matter in a box with periodic boundary conditions. And this you can control by lattice QCD data. That's what I will also discuss later. Or you can consider non-equilibrium dynamics and really perform fully heavy ion collisions covering all phases, and from an initial phase up to the final phase, and let's say pass off all stages of interaction from microscopic point of view, propagate explicitly the degrees of freedom and consider the interaction. Of course, in this case, it's a very complicated approaches and they can be solved only by Monte Carlo simulations. And that's what I will talk about today also. And in this case, the goal of such type of microscopic approaches to provide a microscopic transport description of the Partonic and hadronic phases of heavy ion collisions. But of course, if you have such goal, you have a couple of problems and questions which you have to answer. First of all, what are the properties of QGP degrees of freedom? And how to solve hadronization problem, and what is an appropriate theory. And that's what I'm going step by step to discuss in my talk. So, and let's start with the basic things. And we know our knowledge on the properties of QGP is based nowadays on the lattice QCD data, which mainly available at baryon chemical potential 0. And what we know that according to the lattice QCD, we have a deconfined phase transition with increasing temperature. And this plot is well known. It's showing you pressure divided by T in the power of 4 versus the temperature. And here you see that at temperature around 156 MeV, we have a transition from hadrons to QGP. Even maybe I shouldn't say transition because it's a crossover. Also, we know there is a chiral symmetry restoration with increasing temperature, and the right plot show you the chiral, show you the scalar quark condensate in view, which is can be considered as an order parameter for restoration of chiral symmetry. And if chiral condensate is non-zero, so then chiral symmetry is not restored, and if it's going to 0, we have a chiral symmetry restoration. And what this plot shows that with increasing temperature, we are approaching chiral symmetry restoration. What we know also that the both transitions occur at about the same temperature for a low chemical potential. But of course, interesting issue is to explore also the phase diagram at a large baryon chemical potential, because here we expect some interesting features like probably existing of the critical point or possible first order phase transition. And there are many theoretical models and speculations in this respect. But what we know by sure from lattice calculation, which is our Bible. So from lattice, we know that phase diagram looks like that, and lattice knowledge presently provides us information up to baryonic chemical potential around 400 MeV, because presently lattice cannot explore larger baryon chemical potential due to the famous sign problem of lattice QCD, and we had a couple of talks in terms of these colloquiums series and about this. And unfortunately, we cannot explore these large MeV phases. And there is another problems. Lattice QCD tells us about the equation of state, for example. And but the problem is, in order to perform a fully microscopic treatment of the heavy ion collisions, we need not only the equation of state, we need to interpret them in terms of degrees of freedom, their properties and their interactions. And that is the main problem. And well, in the last millennium, our knowledge was based on PQCD for weakly interacting system of massless quark and gluons. But nowadays, this paradigm doesn't hold anymore, because as we know from PQCD calculation, which is depicted as a yellow arrow bar in this plot, if you go closer to the critical temperature, we come to non-perturbative QCD regime. And here, perturbative expansion doesn't work well. So, and it means that we are dealing already with a thermal QCD, and it's a QCD at high Parton density. And here we have a strongly interacting system, which could be interpreted in terms of quasi-particles, some effective degrees of freedom of massive quarks and gluons. And it means that how we presently can solve this problem, we can build some effective models, which should reflect finally the equation of state of lattice QCD. And such model has been built. It's a dynamical quasi-particle model. And the dynamical quasi-particle model, it's effective model, of course, for the description of non-perturbative, strongly interacting QCD based on the lattice QCD equation of state. The degrees of freedom here are strongly interacting dynamical quasi-particles, quarks and gluons. And the basic ideas of these models is related to some single particle green function or quarks and gluons propagator, which are depicted here. And they have a complex self-energies, as you see here. And it means that the properties of your quasi-particles, they would be specified by the scalar complex self-energies. And the real part of self-energies related to the thermal masses of the quarks and gluons. And the imaginary part gives you information about the interaction width of your quasi-particles. And that actually means instead of massless quark and gluons in PQCD, we are dealing here with a broad, strongly interacting quasi-particles with a spectral function of Lorentzian shape as depicted here. And this your dispersion relation are far off shell dispersion relation. And here just example of the spectral function as a function of energy and momentum, which became independent quantities now. And this model has been developed by Wolfgang Kassing and Andrea Pischir in 2005. And after that, it was a couple of work showing thermodynamic consistency of this work and these extensions and so on. And I will tell you about the latest stages of this model. But of course, you have some effective model, and the issue is how you realize it. What is the basic idea? How you come to the physics? And here I just depicted the basic ideas, how we realize it. So you start with some propagator and some form, but since it's effective model, you need to introduce some ansatz for the temperature and baryon chemical dependencies of masses and widths. And this ansatz is, in our case, it's motivated by hard thermal loop. I will show that. We need some ansatz for coupling constant, which is would be based on QCD lattice data for entropy density. We need some scaling hypothesis how to provide the critical temperature as a function of baryon chemical potentials, this relation. And then when you make these ansatz, what you can actually do? Now you can evaluate fully the QGP thermodynamic in equilibrium using Kadanoff-Baym theory. And after that, you can compute your thermodynamic quantity, such as the entropy, density, pressure, and so on. And you can, by comparing with lattice QCD data at zero baryon chemical potential, to fix your few parameters in the model. And then, of course, when you are done and you hope that your assumptions are okay, you can explore the properties of QGP in TMUB plane. So that is a strategy. Now let me open these boxes step by step. Let's start with modeling of the masses and widths. As I said, it's inspired by hard thermal loop. And here we have explicit form depicted here. Here you see that the masses are square proportional G square T square, and G, it's a coupling constant. And what we have also, we have a width, which also depends on G square, and log, which is also contains G square here. The basic issue how to do model the coupling constant. And in the latest version of DQPM, we do the following strategy. We just relate coupling constant to the entropy density as a function of temperature and zero baryon chemical potential. For the entropy density, which entering this formula, we just took parameterization of lattice QCD data. And then we have these parameters which should be obtained later on. And additionally, in the full theory, you have only one parameter C. So the number of parameters is really, let's say, very small. It's one parameter C and parameters which entering in this feed. That's all. That's all, really all related to the parameters. Now, we need a scaling hypothesis for the effective temperature, which is chosen in the following way. And by that, we can relate the coupling constant at mu equals 0 to the coupling constant at finite baryon chemical potential. And the critical temperature is obtained by assuming a constant energy density for the system at Tc mu q, where the energy density at mu q equals 0 is fixed by lattice QCD data. By using this assumption, we obtain the following expression for the Tc mu q dependencies, which were later on appears the lattice data, and we were very glad that it's very nicely agrees with the lattice data. And in this plot, we show comparison of DQPM T mu bu dependence here versus the some lattice result, which are depicted as red and these cyan lines. And you see up to this point, it's very nicely agrees with the lattice result. So good, now we defined model. Now we can compute entropy and baryon density in quasi-particle limit, which has been developed by Gordon-Baym in 98. And there are very nice paper from Lizot, Yanko, Rebhan, and other authors also working on this topic. And here you can compute entropy density and baryon density. Here you see your propagators and self-energies. And that is a result of our calculations when we feed our parameters to the lattice QCD data at zero baryon chemical potential. Here, of course, nice, but you must understand that is because we feed our parameter to that. But that is already a result. So, and here, using our mass dependence on temperature, baryon chemical potential, and our assumptions, our scaling hypothesis, and so on, we obtained already result for finite baryon chemical potential and compare with existing lattice QCD data from BMW collaboration here at mu b equal 0.4, and you see also rather good agreement. So it gives us a confidence that this model can be used for our goals. And our goals, we need the properties of the degrees of freedom and their interactions in order to proceed with heavy ion simulations and calculations. Okay, using all of these parameter fix, we can now plot what is our proper Parton properties. And this plot showing you the masses of quarks and low plot gluons as a function of temperature for different baryon chemical potential. And also the low part shows the width of quarks and gluons. And this plot showing you coupling constant as a function of T mu B. And here it's scaled over Tc. One can see that, of course, if you increase baryon chemical potential, the critical temperature going down and also the masses are going down. And however, for the width, this dependence is not very strong in our model. And here you see again example of some Lorentzian spectral function for some twice critical temperature, but it's for 0 baryon chemical potential. Now, what we need also the interactions of our degrees of freedom. And if in the first PhD paper we relate the interaction cross-section directly to the width, in the later paper we want to use the more sophisticated things, because in this case what we also want to keep, we need some kind of square root of S dependence, we need angular dependence for these cross-sections, and how to obtain it. And for that we calculated the Partonic cross-section using leading order diagrams, and which are depicted here for quark scattering, gluon quark scattering, gluon scattering, and so on. But the differences here to the PQCD type of calculation is that here we have definitely non-perturbative approaches, and our propagators looks different. You see, it has a width here, it has imaginary part here, and in some cases you can think about that our effective model could be related to so-called resum propagator. We don't do any resummation, of course. It's effective model which we feed to the full lattice calculation, which contains everything, all order of everything. But we feed the properties of our, let's say, self-energies such that it feeds the full lattice calculation. And in this case, you could think about so-called effectively resum theory. So, and in this case, we think that our leading order diagrams should be rather good approximation, because here we have so-called resum propagators. Now, of course, it's a hard work to compute all of that. And here, of course, all credits goes to Pierre Moreau, who did this work, and it was part of his PhD thesis. And I show just only some plots from his work. And this plot demonstrates differential cross-section for some particular channel, UU going to UU scattering, UD going to UD, here U glue to U glue, 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 glue. And of course, it's behave optically different because it's a combination, either it's T, U, S channels, and so there are different combinations. And here you see solid line, which corresponds different square root of S, different energies, and also dashed line, which corresponds to so-called on-shell calculations and off-shell. Let me explain what I mean by on-shell. Here you see the scattering of two quarks, for example, 1 and 2 scatter, and here you have elastic scattering, and here it's a theta, it's angle of your scattering. And on-shell corresponds that you, for example, put all particles on their pole masses. They all have spectral function as depicted here, but you put everything on the pole masses. And under off-shell calculation, I mean the following. For initial particle, we have to select some masses. So we select the pole masses, but the final particles, they could have any masses, so it's a cross-section integrated over spectral function of the final particles. And that is the difference between solid and dashed line. And you see, it's not very big, but rather visible, especially if you play with the masses of initial particles. So, and what I want to say here also that in this case, our angular distribution are much more in direction of isotropic compared to forward PQCD calculation. And it means that our scattering would be much more effective to change angular momentum also of the particles. Okay, now I just demonstrate on this plot the total cross-section again for on-shell, off-shell cases. On the left plot, it's showing you the total cross-section as a function of the square root of S. And you see rather shallow dependence, but the different color lines corresponds to different temperature. And you see that cross-section has a strong temperature dependence and going down with the temperature quite a lot. And the next plot showing the dependence on the square root of S versus the baryon chemical potential. And here you see this dependence is not very big. And this will be reflected and coming back with the results for heavy ion collision and for transport coefficients. And the right plot showing the square root of S dependence with respect to flavor chemistry of different channels. And here you see very big differences because for some channels it's only T channel holds, for another it's combination TU and so on. That's rather big dependence on the flavor. Okay. Now, what is another important issue with this quasi-particle model, and this is the principal differences of this quasi-particle model from other on the market, because it has a width, and in this case, you have a space-like and time-like of your spectral function. And you can even calculate mean field properties, mean field potential of your quasi-particles, because you can, with such projection operator, you can separate space-like part of energy momentum tensor, and it will define the potential energy density. And here you sum up space-like gluons, quark, antiquarks. And it means that in terms of 1 pi approach, and the full DQPM, it's in 2 pi approach, but here in terms of mean field 1 pi approach, you can define your scalar potential, mean field potential, which could be related to Parton scalar density. And what turns out in quasi-particle potentials are repulsive. And in this case, it means that the force acting on quasi-particle, they accelerate particles. And this would be important for building V2 for heavy ions. Okay, now with introducing your dynamical quasi-particle model, I can come to transport properties, which define the properties of QGP near the equilibrium. And I wanted to start with the example of hydrodynamics models because it's for many people, it's close to the heart. So, and here in hydrodynamical, of course, viscous hydrodynamical model, you need transport coefficients which enter your hydrodynamical equation like shear viscosity, bulk viscosity, and diffusion coefficients. And is for the hydrodynamical model, they are input for hydrodynamical model. You need some extra model to define this parameter. And here just shows the meaning of this transport coefficient, which defines the properties of your fluid and how it's involves with respect to, let's say, deformation, expansion, or diffusion properties. And let's start with the shear viscosity, because it's a very interesting transport coefficient which related to the resistances to the flow or to the friction forces as depicted here. And here I show this famous plot from Roy Lacey, Arkady Taranenko, when they show the sample of eta over S versus the temperature for different liquids or for different substances known on the Earth. And here you see, for example, water. And what turns out that according to the experimental data, which cannot be, of course, they cannot measure this directly, but it could be related to measurement of elliptic flow with the help of hydrodynamical calculation, you can get some constraint on the possible eta over S. And it turns out that eta over S measured in heavy ion collision is very small. It also relates to available lattice data. And it tells us the QGP, it's close to ideal liquid and not in the gas or weakly interacting particle. So QGP is a strongly interacting matter. And here I just want to give some very interesting income from the recent paper by PQCD community, so who made an investigation of pure young males PQCD calculations when you have only gluons. And what we know, if you have a leading order, eta over S in this case is rather large near TC. But recently it was a paper by these authors, and when they perform a next leading order calculation, and what they show that next leading order calculation can change your result by factor of 3. And what is this really important message? And here it was, as just I copied from their paper, this conclusion, that perturbative expansion is problematic even up to 100 GeV. So, and it means that how we can proceed. And the preposition is we have to rely on effective models of QCD. That's what we are doing now. So now, of course, having all of that, we can calculate transport coefficient with a dynamical quasi-particle model. And here we start with a eta over S ratio as a function of temperature, and this plot showing you our result computed with a relaxation time approximation, and that is a famous formula where we have tau, it's a relaxation time, and here you have a two different line in dashed green and red line, and they correspond to two cases. In one case we compute a relaxation time which is over proportional to the interaction rate, which was calculated from by solving microscopic collision integral, and it's related to the calculation of all, let's say, possible interactions on the system, and by using the cross sections which we computed. And the second line corresponds when we take tau just 1 over proportional gamma mu, which enters in our spectral function. And what we find, and there is a good consistency between two calculations. Moreover, we used in this paper other method which related to the Kubo formalism, and in these cases, it's related to field correlator, calculation of field correlator, but what we also obtain is a good agreement between all of these approaches. Moreover, here you see these light blue lines, which corresponds to Bayesian analysis by Stefan Baas group. And what we all of these calculations showing that definitely eta over S in this case has a rather small value closer to TC, and agrees with the lattice calculation, lattice data from a TEP group. And on a left plot, we already can explore our mu-b dependence, and here it's a calculation for finite mu-b. But what we see here, we obtain only weak dependence of shear viscosity over mu-b. Now we can proceed the same with the bulk viscosity, and this plot showing you again our result for the bulk viscosity calculations with DQPM in comparison to the lattice QCD data, which is depicted here. And here we also compare to some conformal holographic models and Bayesian analysis from Stefan Baas group. And on the left plot, we show again mu-b dependence of the bulk viscosity over entropy ratios. And what we see again, we have a weak dependence of bulk viscosity on mu-b. And the last transport coefficient, what I want to show today, related to the electric conductivity. And the electric conductivity is rather interesting transport coefficient because it's directly related to the photon and dilepton yield. And this could be have a, let's say, direct impact on conductivity properties of your system. And this plot showing again comparison with the lattice data, and what we see at mu bu equals 0, we again in a good agreement with the lattice data. But what turns out that QCD matter, even at TC, is a much better electric conductor than known substances as a copper, argon at room temperature by huge factor up to 500. So now, it was about the properties in the DQPM, and which we used close to equilibrium. And now I want to come to non-equilibrium situation. And of course, as soon as you dealing with, you want to describe the properties of QGP, you have already some concern that you are dealing with a strongly interacting system. And your degrees of freedom now, it's addressed partons. And it means that you have a hard time to apply the standard transport theory, which we are used for low energy physics and let's say like Boltzmann-Uhlenbeck approaches and so on. And the same holds for hadronic matter, because even if you consider hadronic matter at finite temperature baryon chemical potential, we now know from many body chiral theories and so on that the properties of our hadrons are modified very strongly in the medium. And here just pick up some example about the K star spectral function for different baryon densities from Barcelona-Valencia group. And you see at zero density, it's a rather narrow peak, but with increasing of density, we have a rather complicated spectral function, which is broad, changing their properties dynamically. Okay, and many body theory tells us as soon as we have strong interaction, we have a large width, short lifetime, we have a broad spectral function, we have a quantum object. And of course, how to describe the broad, strongly interacting quantum system and transport theory. And as I mentioned, we have to departure of semi-classical BU equation. And what we have to do, we have to come back to real theory, which is quantum theory. It's Kadanoff-Baym equations, and proceed in this way. Of course, I have no time on this colloquium to come to the details of this approach and of this theory, but I just want to remind the basic ideas. And Kadanoff-Baym equation is written in terms of green functions as smaller. And here what you see entering in this very formal way of writing very complicated Kadanoff-Baym equation, you have also the self energies, and they are also complex. And here is just definition of all these green function and self energies, and with respect to the time ordering your field operators. And I just want to mention that this theory has been developed already in '62 by Leo Kadanoff and Gordon Baym, and published in this very fantastic book, which I recommend to everybody to read. And how we can use it in practice. What we do in transport theory. Of course, we have to do some simplification. What we do a Wigner transformation of Kadanoff-Baym equation and go in momentum space in one variable, and then we do first order gradient expansion, and then we separate real imaginary path, and one can obtain such generalized transport equation, and which is written for green function as smaller here. And if you look on this structure, you can recognize here already parts which you are rather familiar from BU type of equation. Here you have a drift term, which relates to the free propagation of particles. You have a Vlasov term, which relates to the self-generated mean field potential. On the right side, you have a collision term, which is a gain term and the loss term. But there is a principal differences in this equation, because what appears so-called backflow term. And if you see, it's related to real part of retarded green function here. And this term reflects the off-shell behavior of your particles by propagation through the medium. And it's vanishing in the quasi-particle limit, for example, if your spectral function related to delta function, or if your spectral function doesn't change properties in the medium. And what is very important here to understand that Kadanoff-Baym equation propagates the green function, which could be interpreted in terms of the product of spectral function and the number of particles. So it's contrary to phase space distribution function of BU equation. Here, green function contains the information about the number of particle occupation probability and the properties of your particles in terms of the spectral function, which is depicted here. And of course, you have these widths of spectral function, which could be related to the lifetime of your system. But it's a nice equation, but again, in order to solve that, you have to do, again, something. And what we do really on the computer, we do test particle ansatz for the real values of real quantities, I as smaller. And here we approximate this quantity in terms of the product of the delta functions. And then if you substitute this solution into this equation, you can solve it formally and obtain the following propagation equation, which has been obtained by Wolfgang Kassing and Sasha Joachim in this paper. And if you compare to the classical equation of motion, you see that there are additional terms which have a very complicated structure and related to the precisely appearance of this backflow term and propagation of your particles in the medium. Okay. But now you can say that you know how to propagate the particles, but it's not all, because you have to change also your collision term. And here, it's getting more complication because it appears extra integration over the energies or masses, which became independent variables due to the off-shell dispersion relation now. And additionally, what appears here, you have a products of all spectral function of your degrees of freedom. And here it's 2 to 2 reactions as an example. And of course, in order to be fully self-consistent and so on, we need to know the medium transition amplitude also, this quantity here with the full glory. And that's, of course, unfortunately, it's very difficult to obtain, especially if you're coming to hadronic world. And what we know nowadays, some spectral function, for example, for the strangeness degrees of freedom, that's what we are doing for raw meson and so on. But there are, it's really very complicated, many body calculations which are required to be done here. So we are standing sometimes with some approximations in this respect. Now we are well equipped, we can put all things together, and now I give you some in one slide, the basic idea of Parton-Hadron-String-Dynamics. It's our microscopic transport approach. It's non-equilibrium microscopic transport approach for the description of strongly interacting Partonic and hadronic matter created in heavy ion collisions. In dynamics is based on solution of generalized off-shell transport equation derived from Kadanoff-Baym many-body theory, as I briefly demonstrated. And the idea is like that. So you start with really initial collisions, for example, gold-gold collisions or whatever, like indicated in this plot. You initialize your nuclei with some Wood-Saxon distribution. You have only nucleons in the beginning and so on. Then you let the system propagate, collide, and in the primary collisions, you pull a string, which we describe in terms of Lund string model. And here you have your leading partons, and here you have a so-called newly produced particles. And what we do how we perform the formation of QGP, we calculate the local energy density in each local cells. And if we find that the energy density is above critical, we dissolving these newly produced prehadrons to partons. And now we know the properties of these partons from dynamical quasi-particle models, and we know the properties of these degrees of freedom and their interactions, and we can do full dynamics. We know equation to propagate it, we know collision term, and so on. And another problem, which I just only briefly mentioned, is of course hadronization. And if you have on-shell particles, it's practically impossible to solve a hadronization problem without violation either energy or momentum conservation. Here you have off-shell particles and off-shell hadrons in the final state. And since you have a spectral function, you always find a solution because you put two off-shell states to another off-shell states. It's very nice because in this case, hadronization keeps strictly for momentum in all quantum number conservations. And of course, in the hadronic phase, we have the standard all hadron-hadron interaction, and in our case, involving this also in medium effects with off-shell spectral function, off-shell cross-sections, and so on. So that's our dynamical model, and now let me show you some results. And let me firstly show some movie from Pierre. You start with the gold-gold collision at weak energies, and that is a section view that you see something. Now we are approaching, and of course, in this case, a system starts to overlap, and here you have a production of quarks and gluons. Then system expands, and already on peripheral part of your reaction, hadronization occurs. You have mesons and hadrons and baryons produced. System expands further, and that's what comes finally to your detector. So, of course, the relevant issue is what is the fraction of Partonic matter you probe in heavy ion collisions. And this plot showing this fraction of Partonic energy density, Partonic energy, sorry, for the time evolution of a system in heavy ion collisions for different energies. That's up to SPS energies, and here it's top Ric energies. And what we see at top Ric energies, the Partonic fraction achieves 90% of the matter and holds for a couple of Fermi over C. And of course, if you go down in energy, the fraction, Partonic fraction is also going down substantially. And that one has to keep in mind. And of course, it's nice, but what we also have to deal in realistic heavy ion collision, we have a huge fluctuation of energy density. In this plot, just showing one PHSD event for central collision. And here you see Z and Y evolution, and here you see X and Y evolution, and you see very spiky contributions. And that is, of course, for only one, let's say, events. And in order to compute mean field properties, you have to simulate many events simultaneously, and they communicate between each other in terms of mean field properties. So, and it's just, let's say, classical plot show to demonstrate the impact of the accounting of quark-gluon plasma, and it's showing the spectra, MT spectra of different mesons, pions, K plus, K minuses for different energies. And look, for example, let's look on the top Ric energies, and the thin line showing you HSD calculation where there is no quark-gluon plasma, and the solid line showing you PHSD calculation when we have a quark-gluon plasma. And this, you see, Partonic interaction turns to be rather important for building of pressure. And that's, you can see even better looking for anisotropy coefficients like V2, elliptic flow, and so on. And here, just reminder that in this case, interaction between constituents leads to the pressure gradient, which is where the spatial asymmetry by interactions comes to the asymmetry in momentum space. And you can make such expansion in the angular distribution and subtract these coefficients, which characterize your distortion of your momentum distribution. And the elliptic flow had a very, I think, important impact on heavy ion physics, because after the first Rig measurement, what we know, it was a great success of ideal hydrodynamic models. And here just some historical example from Uli Hein's calculations, when he computed the V2 as a function of transverse momentum for different particles. And you see nice description up to transverse momentum of 1 or 2 pt. However, the ideal hydrodynamical calculation continued to grow. And then it was another important paper by Paul Ramachke and collaborators, which shows that one has to take into account viscous corrections. And if you do viscous hydrodynamics, then your distribution starts to bend down. And by changing it OS, you can even, let's say, relate measurement of V2 to the eta over S quantity. So that's what we do, is important observables, which is relating elliptic flow to the eta over S in the system. And here we show our PhD result for V2 as a function of square root of S. Again, on the left part, we show two calculations. The blue line, it's without quark-gluon plasma, red line with quark-gluon plasma. And you see that in this case, especially at high energy, building of pressure is definitely related to QGP, interactions. And that was our eta over S, historically calculated in a box with periodic boundary condition. It's real PhD in a box, and computed with a Kuba method and relaxation time approximation, and compare also to Bayesian analysis. And as you see, definitely it's also showing direct impact of, let's say, interaction in the quark-gluon plasma on the elliptic flow. But in our case, let me say again, we calculated OS for transport theory. It's not an input like in hydrodynamics. In our case, all done dynamically. Really, we calculate all interactions of our degrees of freedom in terms of cross-section and potential interactions. So, and what is also important, that potential interaction is also important for V2 and pulling this distribution up quite a lot. Okay, as a just example, I flash our calculation for LHC, which also shows, and for VN, V2, V3, V4, V5 with PhD, and they show good agreement. But finally, I want to come now to the my final part of my talk, which showing the traces of QGP at finite μ in the observables of heavy ion collisions. And the question is, how in heavy ion collisions we can define what is the temperature and baryon chemical potential? Because for heavy ion collision, it's not natural properties. What we can calculate in heavy ion collision, we can calculate energy density and baryon density, just counting the particles and their energy in some volume, right? So, but we have in a reliable way to subtract from this temperature and baryon chemical potential in order to relate our properties of our degrees of freedom and their interactions. How it's done? For that, we use a lattice QCD result and the Taylor expansion for baryon density and for the energy density in terms of susceptibilities. And what we actually do, we calculate in each cell of PhD, it is depicted some example here, it's spiky distributions. We calculate the energy density and the baryon density, and then by solving this couple equation numerically, we obtain in each cell temperature and baryon chemical potential. How it looks in reality, it's again some plot showing you what we obtain by that. This plot showing you a simulation for gold-gold collisions at square root of s 19,6 GeV for b equal 2. And here this is a plot showing different time, 1, 2, 4, 8 Fermi over C. And the middle part showing how temperature develops as a function of time, and the low plot showing you how the baryon chemical potential develops as a function of time. And what you see, it's rather inhomogeneous distributions what is appearing here. Well, one can look also on T mu B trajectory in this case. It's our critical line in PhD, and here it's real simulations for which showing you T and mu B for cells, where we selected only cells with the rapidity of the cell less than 0.5 and temperature larger, of course, than critical temperature. And here you see this trajectory with the time moving to the left part, and here it's already hadronization starts to later on occurs, and you come to the hadronic world. But what you see in this case, you probe baryon chemical potential, which are not incredibly large in this case. So in the QGP phase, so that is related to QGP part of the story. Well, now we can, how we obtain this information. We have to compare with our PhD approach in the different options. I will show you some result where the color coding would be corresponds to what is written on this slide. In the green line, we're showing the result from what we call PhD 40, where we took into account only temperature dependence of our cross sections and also the properties of quarks and gluons were counted only as a function of temperature, and these cross-sections were subtracted in this case just related to the widths of the degrees of freedom, and it has the following form. And then in the blue lines would correspond to PhD, what we call 50 result, when we take into account already cross-section, as I explained before, calculating, which were calculated by these diagrams. And in this case, we take square root of S dependence, and that's, but we take the baryon chemical potential equal to 0, and in the red part we have the full glory with the full mu B and T dependence. And here I just show you some result of calculations. Let's start with the top rig calculations. This plot show you repeated distributions, this PT spectra of pions, kaons, proton, antiprotons, lambdas, antilambdas, and again different color code. You can see, just concentrate on comparison of different color lines. You don't see big differences. So it's not a big surprise because at Rig energies, your baryon chemical potential is very small. Let's decrease energy. And let's go to the top SPS energies, 156 kinetic energy. And here actually you see again rather similar behavior. And only for antibaryon sector, we see some tiny small differences, but these differences more related to the differences in the calculation of cross sections. So we count here the square root of S dependence and angular dependence of our cross section, which gives us slightest differences more than the accounting for baryon chemical potential. And that's also understandable because if you now decrease the kinetic energy of your collision, then the let's say the energy, the fraction of QGP drastically going down. And of course, the influence of this QGP on the final observables is getting small, unfortunately. And this you see if you go down in energy, it's the same. So I just flashed this plot because that's what I want to say in this message. If you go even to very low energy, here, again, the fraction of QGP is very small. So conclusion is it's very weak dependence of bulk observables on mu B. Let's look now on a more comprehensive probe like elliptic flow and directed flow. And in this case, what we have for elliptic flow as a function of pseudo-rapidity for charge hadrons, again, all our three lines lie on the top of each other. Okay, that's a pity. Let's look in a little bit more detail. And if you look on non-weighted contribution of this V2, just calculate what is the V2 of hadrons which came directly from QGP without, let's say, accounting for further weighting. And you see that in V2 of particles coming of QGP is bigger than those which come, for example, from decay and so on. But if you take into account the relative weight of this contribution, it turns out that, let's say, the QGP would be rather suppressed because all of the particles which come from hadronization, they suffer from further interactions and formation of some resonance. For example, pi goes to rho, pi k goes to k star, and so on. And that's spoiling the message about the QGP V2. But then we look also on the V2 of baryon and antibaryon already, not for charged particles are here, but making a more comprehensive analysis. And here we again see small differences in the V2 between the different approaches. And on the right part, it's also for different energies. You see small differences, and especially these differences are more visible for antibaryons and baryons than for mesons. And that is also result for V1 coefficients. Here we see a little bit more sensitivity because V1 is also rather sensitive to the angular distribution of your degrees of freedom. And this angular distribution in the Partonic phase has a small impact on the final V1. But again, we totally see a weak dependence. And I'm coming to my conclusions. So that's which I call more messages, let's say. And what we investigated, so that is a TMUB dependence of Partonic cross sections and masses and widths, which we implemented in PHSD. At high MUB region, we probe is probed at high MUB region is probed at low bombarding energies or high rapidity regions also. And what we obtain only very weak dependence on MUB. If you look on the bulk observables, and we see some small dependence on MUB for the flow harmonic V1 and V2, and more pronounced dependence related to square root of S dependence of Partonic cross section and their angular distribution. And that is precisely understandable because fraction of QGP growing down with the energy where baryon chemical potential is getting important. And moreover, if you remember the first part of my talk where I showed the transport coefficient and especially cross sections, they have very rather weak MUB dependence in our quasi-particle models. And of course, as an outlook, I can say we definitely need a more precise equation of state. Larger MUB might be here. We will figure out some surprises, or maybe it would be first order phase transition at some finite MUB. But what we see now, it would be rather challenging task for upcoming experimental at FAIR, NICA, or Beam Energy Scan at RIG to explore this MUB dependence of the QGP properties. So, and as a finally, I want to thank all people who worked on this project, and especially to Pierre Moreau and Olga Solovyova, who made a lot of calculation, which I have shown today, and also all our collaborators. And I'm really grateful to all of you for following me in this day. Thank you very much.
Well, thank you. Thank you very much for a very nice presentation. We have some people already wanted to ask questions. So let me start with Kirill Bogoslavsky. Go ahead.
Hello, thank you very much for the very nice presentation. I have already actually had a few questions. Actually, I also asked them in the chat window, and there were a couple of discussions actually during the talk.
I'm sorry that I could not follow.
No. I'm very sorry. So my questions were at first about the quark-gluon plasma model that you use, and I was told that it's by Olga Solovyova, I think, that it's actually using Coulomb gauge and transverse propagators. So my question is now related to that. Basically, instead of, I mean, you could go to this to the small width limit of kinetic theory, which just means that instead of having peaks with some lifetime or gluons with some lifetime, you have just delta peaks. But on the other hand, HTL has some or kinetic theory, effective kinetic theory has a very strong resummation of collision kernels, like which is important for the LPM effect, for instance. In your case, as far as understood, you use Kadanoff-Baym equations for propagators without Landau damping, just having a mass and a width, and I think only you use transverse gluons, not longitudinal ones. And in your Kadanoff-Baym equations, I don't think you are able to resum, because they're very complicated ones. You can resum and get the whole LPM effect correctly. Maybe I'm wrong, but I'm just asking that. So basically, what happens if you set your damping, your width, to 0? You then should be very close to kinetic theory in some sense. Do you still get the same results, or
yes, if for example we let's say yes, if we set the widths to 0, or if we set the masses to 0, we should reproduce, and in this case PQCD type of results. Yes, of course. So, but what you said is actually absolutely true. Yes, of course, it's an effective model. So that's we stay with this limitation on a moment. One can develop it might be further, but from the other hand, keep in mind it's effective model constructed for practical purpose. So
okay,
of course it would be absolutely great to have a state-of-art first principle ab initio calculations, and as soon as we have it, we don't need such type of model. I would be happy to take real let's say lattice QCD result when they provide us properties of the particle in Minkowski space, and then we don't need all of these exercises.
Okay, can I just follow up before this is a very short one?
Sure, go ahead.
So especially on slide 15, where you actually show that you use the model almost up to TC, so basically going down pretty low temperatures. Now, do you how important is something like the width, for instance? So when you is it a very essential parameter in your
it's
model?
Essential parameter. Let me put it's a rather essential parameter. Without width, you can never get this minima in eta over s. You would be high up. So
okay, so this basically gives you the possibility to go to small temperatures.
Exactly, because without width you would be like all PQCD result high up. So in this case, width is very important for us. Yes. So yeah.
Thank you very much.
Okay, next question. I think Rajiv Singh was the next to ask. Go ahead.
Yeah, I have a very small question regarding off-cell and on-cell cross-section, which I might have missed. The question is that isn't it that for lower collisional energies, on-cell cross-sections is more than the off-cell?
At low energy collisions.
Okay.
Well, yes and no, because look, in this case, if you for on-shell cross sections, it depends on also very strongly on square root of s what you probe. Yes, if you have a low energy collisions and you consider, like in this example, for the initial particles I took, even if I call off-shell cross-section, for initial particles I took a pole mass. But if I take a smaller masses, this could be different, because in these cases that more phase space will be open. So, and it has a non-trivial dependence.
So basically, it depends on what masses you take initially.
Yeah, but in you see, when we compute the transport properties, for example, eta over s, we take into account also initial spectral function for these initial quarks. Or if we do PHSD calculations, then we definitely know the masses of incoming particle, because in this case you treat them dynamically. Each quark has a certain mass according to the spectral function selected by Monte Carlo. If they scatter, final quarks you treat in the following way. It's test particles. You put them on some certain mass according to the spectral function which you play by Monte Carlo.
Okay, thank you.
Okay, the next question is from Dmitro Olenichenko. He asked me to read the question on his behalf. So he asked, are you able to reproduce the measure dV1 over dy as a square root of s minimum for protons? I think you showed that you can.
Just a second.
Sure.
That which
V1,
ratio? V1
as a function of rapidity, I assume. Sorry, dV1 dy as a square root of s. I assume that's what it says. I'm just reading it.
V1 he wants precisely for protons. Yeah, so
for protons,
I think
for in that dependence.
How to say, I don't have this. It's approximately goes in the right direction, yes, but I didn't show this plot in this talk. Sorry, I don't have a corresponding slide. Yeah.
I guess in this case,
it follows. It follows. Yeah. Of course, we made this particular study. It was a couple of papers by our Gießen collaborators in those time, Volodya Konchenkovsky, Wolfgang Kassing, and our Dubna collaborators, Slava Taneyev and Vadim Voronyuk, and they made this investigation of precisely, they studied the minima of V1 of protons, and in PHSD, yes, you reproduce this minima with relatively qualitatively. It's not going through the middle of the point, but qualitatively it goes very in the right direction. So, and it's without QGP, you cannot go in the right direction at high energy. At low energy, I should say, potential plays a role, and especially for protons. And here, this playing with hadronic potential, it's not easy business, and it's also important for these issues. It's in our publication. I can give reference if it's interesting.
Okay, sounds good. Sounds good. Now there is another question from Masoud Shokri. He asked me also to read a question on his behalf. What happens to mu with evolution? I assume sort of in more detail, if you could describe what happens.
To mu b, right?
Mu. Well, I assume it's baryon.
Yeah, it's mu b. Well, in my well, here I'm coming. What's happened with mu b? It's very much depends on the energy. Here in this example, which I depicted here, you see you start with a mu b, which is covering this range. It's never a point, like in a statistical model, let's say you hit the point and that's all. It's quite a wide range. And this is don't forget, that is a very particular selection what we did. If you use a different selection, you would cover the full range or whatever. But here we just wanted to see really for slow cells when the this thermodynamical quantity can be subtracted in the best way what we can do, related to this lattice result using susceptibility expansion, as I have shown. And here you have a rather wide range in the baryon chemical potential, and but with the time, of course, it's squeezing to disappearing because you come to the phase transition. If you start calculations at, for example, LHC, you would be just on this line. We have such plots, or a tree could just close to this line.
So pretty much zero chemical
Yeah,
potential.
pretty much zero. The point is, if you go to more low energies, here it's ⁻⁷ 17 GeV. We also have such plot, but the point is, in this case, the fraction of QGP is so small that it's already also losing its relative importance. So for demonstration, we choose this intermediate energy, or in this plot, it was also energy closer to that. Yeah, so.
I guess that's sufficiently clear. Okay, I don't see any other questions from the audience, but I did have some of the questions that I was sort of marking down when you were talking about the model. So one of the questions that I had myself was actually, when you were building the effective model, essentially you were comparing this to, in a way, like a resummation of infinite series, and of course you get this effective masses and the width in the model, and that seems to be fair. And then you use this to calculate the cross sections, right? Now, my question is sort of simple. Theoretically, it seems like those same cross sections should, in a way, determine the self-energy. So isn't there some sort of self-consistency condition you should impose in the model so that the masses and the width that you determine are actually coming from the cross-sections that you are using?
Absolutely. Later. Yes, super question. Thank you very much. It costed, I think, half of year work of Pierre to check self-consistency of the model. The answer is you achieve approximate self-consistency with all of these effective models. And then, in our papers, there are more detailed plots, which I don't have here, but what I have, and I can show you, maybe it would be convincing. Sorry for flashing this. I know what I'm looking for. Yeah. So, for example, this plot, which is showing a calculation of ETOS, which is in some sense reflecting the strength of interaction, right? And the properties of degrees of freedom. And here you have two lines. The one line, which is this dashed line, corresponds to the calculation of relaxation time, which is one of a proportional of the width, which is in the spectral function, exactly in the self-energy, as you said. And another one, it was computed really, it's nothing else as a interaction rate when we compute all cross sections explicitly and summing up of all of that. And this gives, for this particular case, this line. So there is a discrepancy definitely, but that is might be considered as a level of accuracy of this self-consistency of the model.
I see. Okay, fair enough. So at least obviously that's something that you are definitely.
Yeah, we are aware of that, of course, yes.
Right.
And here it's also, I should mention here, it's also rather complicated underwater rocks, how you compute, for example, the rates for off-shell cases, which is a not well-defined issue. And because what we usually do, we define rates for on-shell cases. And here we have a spectral function and how to deal with all of that. It was rather untrivial, and this definitely require much more, let's say, theoretical income to solve it properly, maybe. Yeah.
Okay. I see there is a raised hand. Kirill Boguslavsky, you want to add something?
Yes, hello once again.
Hello.
Oh, I'm very sorry. I forgot to actually unmute myself before. I have actually a question about the form of the width. So I think there is it's a couple of slides from here. The functional form of that.
Yeah, here.
Yes, exactly. So exactly. So the masses are inspired by HTL calculations, and there, of course, you have this CF factor. I'm sorry, it's a bit more technical as the question. CFG squared factor, and then you have this T squared plus mu squared, etc. The width. Where do you get the? Do you have a reference how you get?
How to say, it was the same, inspired by some hard thermal loop papers when people are using not exactly the same dependence. It's also coming from some expansion things. And we manipulated with that ourselves a little bit. So I would say it's a home product at some things. Not exactly forms that you should have a log here. It's rather trivial. You could get it right. But for example, the C is a parameter. It's exactly our parameter, you see, which we feed finally. And you see here entering G square and G square. Well, in the first papers, we parameterized G square also as in a similar form, also using some formal dependence on T mu B. But later on in this paper, we came to the idea that it's better directly take it from entropy density, because we found some kind of scaling with respect to G. It really scales very beautifully. And then why not to use it, let's say. And well, here it's not exactly direct reference. I can give some reference about, yeah.
So I know from Bratton.
Yeah. It was a papers by, I think, André Pichir, when he played with André Pichir. And it was a year, should be slightly above 2000. I can, if you send me a message, so I think my email should appear somewhere in this. I can look in our first papers of DQPM. It's actually a paper of André Pichir and Wolfgang and PIL, where they well, in those cases, it was slightly different. It was only glue case in this case, quarks appears later in the model. But I can look.
Okay, thank you very much.
Okay, let's see. Any other questions from the audience? I do have one more question. It's more theoretical than the previous one. There is also in the audience, but let's come to that later. So my question is about the DQPM model that you are basically then use in your dynamical model, Parton-Hadron, this model. But when you are using DQPM model, essentially you're extracting the properties of quasi-particles in equilibrium. And of course, it kind of heavily relies on the fact that you are in equilibrium, it's temperature and everything dependence. Now, when you're working out of equilibrium, obviously you're outside of that limit of validity. So are there any words that you kind of say to convince yourself?
Yes, of course, it's a very excellent question. Thank you very much. Well, what I can tell you, if you tell us how we can do better, we will immediately jump on your ideas. So what prevents us is the following, what I can make such example, which I like to make. Imagine some big wave which you have on the sea. You put a rock. On the top of big wave, you have some perturbations. And that's what we hope, that these non-equilibrium effects could be finally for our spectral function properties considered as a, how to say, it's some perturbation, because they are rather broad. And it was some study using FIFO theories, I think, by Wolfgang Kassing collaborators and other people, when they looked for some kind of perturbation properties and so on. But you are absolutely right. We subtract the properties of QGP at equilibrium, and situation is even worse because we have to subtract temperature and baryon chemical potential also of our matter, which is far from equilibrium, let's put like that. And we have to relate it to the equilibrium properties. For that, I have shown you this technique, how we do via equation of state. I didn't have a time to come to the details in order to be a little bit better in the beginning, and when the longitudinal expansion is incredibly huge, and where, of course, the matter is really far from equilibrium. And if you look for component of energy momentum tensor longitudinal pressure and transverse pressure, they are nothing to do with each other. So, and well, but you still need a calculation of energy density and so on. What we do kind of these corrections, trying to remove longitudinal expansion using some technique for that. But well, that is a present situation, of course.
Well,
You're right.
fair enough. I
You're
cannot
right.
suggest anything better, so I'm just
If
asking.
you can suggest, we are really, you are highly welcome, but I don't expect that. We had a talk with our lattice colleagues, and they said you shouldn't expect non-equilibrium lattice calculation in your lifetime. So,
Right.
okay, maybe for new generation, it would be already different level of approaching to the problem.
Okay, we have another question. Xingyang Wang. Go ahead, Xingyang.
Hi. Hear me? Oh.
Yeah.
Yeah.
Okay. I just have a question about, you were showing something using this PHSD model to calculate the flaws for hadrons, like V1, V2. And I'm wondering if we want to match the real experimental data, should we consider the rotation effect? The vorticity may make different for the flaws, I think. And also, I want to ask, do you think it's possible to add the vorticity into your model or easily, or it's pretty complicated? Thank you.
Let me put like that. In our case, I don't need to put anything by hand. That is a microscopic transport description, and all effects, including vorticity, they are naturally coming by interactions. And there is a study with PhD related to vorticity effect. It's a study by our Dubna collaborator. It's Vadim Voronyuk, Slava Taneyev, and also Lucia Oliva. She calculated such things, and she will give a talk next week. And I would recommend you to follow her talk, and then you will see even some plot related to vorticity in PhD. So the answer is, due to the conservation, approximate at least, of angular momentum in our case, the vorticity effect is generated dynamically. We don't need to put anything by hand, but you can study that. And this study has been, to some extent, performed, and there are published results on this issue. Again, I can give you references if you send me a message.
Sounds good. Any other questions? I don't see any other questions, so let me wrap this up. Thank you very much for a very nice presentation, for taking time to prepare it, and thank you.
Thank you, everybody. Yeah, thank you very much. Bye.
Thanks.